of SparkNano. I will introduce SparkNano in a minute, but first I would like to congratulate ATLANT with their 5th anniversary. I believe they had a nice party earlier this year. We also had our 5th anniversary this year, so congratulations on behalf of our company. So very short introduction to SparkNano. We are a Eindhoven-based equipment company. We develop and sell spatial atomic layer deposition equipment, and where we focus on applications in sustainable energy, mainly electrolysis, fuel cells, batteries, and also some photovoltaics. We supply both R&D tools and mass production equipment. This is an example of an R&D 6-inch R&D tool, but we also have sheet-to-sheet and roll-to-roll mass production tools available. If you would like to know more about these products, please contact me, or we're happy to accept your PO, of course. So what we do is spatial atomic layer deposition, and this morning it was already explained a bit by Eric Gessels. Basically, what we do is ALD, but we use a spatial separation of the precursors and co-reactants instead of temporal separation. We do that in a so-called ALD head, which is technically similar to what ATLANT is doing, but then bigger. That's the same size, the same width as the substrate. And it's based on spatial separation of precursors and co-reactants, hence the name spatial ALD. And there has to be a movement between the substrate and the ALD head. So we do this at atmospheric pressure, meaning no vacuum. Of course, it's an inert atmosphere, but we don't use vacuum pumps. This technique can be scalable to large substrates and roll-to-roll processing. And very importantly, deposition rates can be 100 times faster than conventional ALD. And as mentioned, we can do this sheet-to-sheet on a discrete substrate, wafer, glass plate, a piece of polymer, whatever you want. But you can also do this in a roll-to-roll manner. So, as said, we focus on applications in sustainable energy applications. I will give you a few examples. One is PEM electrolysis. PEM electrolysis, PEM stands for proton exchange membrane, is one of the methods used to produce green hydrogen. So, using electricity to split water into hydrogen and oxygen. It's generally made up like this. There's a membrane in the middle, a polymer membrane. On both sides, there is a catalyst layer coated. On one side, it's iridium oxide based, and the other side is platinum based. That is sandwiched in between porous electrodes, and then you apply current, and you get hydrogen. In many countries, also in European Union, there's quite an ambitious roadmap in how much hydrogen we need to produce in the coming decade. And to meet these future demands, we need to drastically reduce cost and increase capacity of all electrolysis, including PEM electrolysis. Important drawback I already mentioned, it makes use of iridium and platinum-based electrocatalysts. Here you can see a cross-section of a single PEM stack. At this moment, the loading of iridium is around 2 milligrams per square centimeter, maybe a little bit less already. But this has to be reduced to below 0.1 milligrams per square centimeter to make it feasible. That's quite a big step. And one way to do that is by moving on to a new concept of making a PEM electrolysis, where the catalyst layer is not coated on the membrane, but actually you use a high surface area porous support, and then you deposit a very thin film, a few nanometers of iridium oxide. So then you have a large surface area, electrochemical surface area, but because the film can be very thin, you can still reach very low loadings. This means, however, that you need to have a method to deposit these iridium oxide films with very precise control of how much material is applied, and also doing that inside porous substrates. There are some examples of iridium oxide processes we did on the titanium porous transport layer, where every individual titanium fiber is coated with a 5 nanometer film of iridium oxide. We also do these things in sort of nanoporous structures. This is nanoporous tin oxide, where this is EDX mapping. Green is silicon, blue is tin, and orangey is iridium. So we can have nice halfway penetration depth control of iridium oxide film. Of course, depositing thin films with high amount of control into porous substrates, ALD is one of the best methods to do that. Another application we're working on, lithium-ion batteries. So yesterday we had a very nice talk by Alex, where he already explained a few of these things. One of the issues, for example, if you want to increase capacity and energy density of lithium-ion batteries, you can use different electrode materials, but reactivity comes back to bite you in the behind. So the cycle lifetime of the batteries can be reduced And very thin ALD coatings, maybe even a few cycles, can help to stabilize these battery electrodes. Again, here, this requires highly conformal deposition inside high porous electrodes with very large surface areas. And again, ALD is, of course, one of the best methods to do that. So what is important in these applications and also others is that we have exact control of how deep we penetrate into the film, how much material we apply, to of course, maximize the performance of the device, but also to minimize waste of critical and scarce materials. I mentioned iridium and platinum are, of course, expensive materials. So, of course, ALD can do this through, we have atomic scale control of film thickness, so that's just based on ALD cycles, but also we can very accurately control how deep we go into the film. Sometimes we need to go all the way down, sometimes we need to be halfway, sometimes we need to stay at the top, but we can control this in an ALD process. So, of course, ALD, as said, is very famous for its ability to coat high aspect ratio structures, and the relation between for things like precursor dose, the precursor concentration and exposure time, and the aspect ratio of a pore has been studied in great detail by many people worldwide. Roy Gordon was one of the first publishing on this topic, and many of ALD experts will recognize relations like this, that in order to conformally coat a pore, you need to apply a precursor with a certain amount of concentration and exposure time, which scales with the square of the aspect ratio, which is the ratio between the depth and the diameter of the pore. So this is true for individual pore. But what happens? There aren't that many applications where you have a 300 millimeter wafer in just one single pore. Mm-hmm. Most cases, you have many of them. So what happens if you have a lot of pores? Here are some examples. This is a funky etched 3D silicon structure. This is actually a battery electrode where you can see there are lots of particles bound together with lots of the tiny pores in between. These are actually examples of porous electrodes used in electrolysis. So it's not just one pore, you have many, many pores. And one thing that happens if you increase the number of pores, you increase the porosity, but you can also increase the surface area, the effective surface area, in terms of square meters per square meter. So here I took just simple cylindrical pores of 40 microns deep, 1 micron diameter. I increased the pore density, so the number of pores per square meter, and then you can calculate porosity and effective surface area. You can see that surface area increases quite a lot. So there's a lot of real estate or a lot of room inside a pore structure if you count all the way from the top to the bottom, of course. That's the play on the Feynman quote. The consequence is, if you want to coat these structures, you also need to supply a lot of precursor, because the amount of precursor that you need to supply scales with the surface area, of course. How much do we actually need? That's actually not that easy to calculate. You have to do a lot of mathematics and modeling and all these kind of things. Don't worry, I will not bother you with complex equations too much. I will just go directly to the results. So for something went wrong here. There's supposed to be one line, but okay, that's okay. That's fine. So for high surface area substrates, actually the expression for the precursor dose needs to be extended if you have a high surface area substrate. It's not only dependent on the square of the aspect ratio, but also on the effective surface area. So what does this mean? Here you can plot the required precursor dose to conformably coat all your pores as a function of the aspect ratio squared, which is then of course a straight line. But if you do that for several different effective surface areas, even though at this point here the aspect ratio in all cases is the same, we do need to increase the precursor dose just because the enhanced surface area. So what does this mean? If you optimize your ALD process on a 1 by 1 square centimeter chip matrix device and you come up with a certain precursor dose to conformably coat a certain aspect ratio, and if you then expect this, you can use the same dose on a high pore density substrate wave, a DRAM wave, whatever, that will not work. So you have to think a bit bigger than that. Well, you can rearrange this equation a little bit in a more practical parameter, at least from our perspective, which is the required precursor mass flow. How many grams per hour do we need to supply? And then if you rearrange it, you can get something like this, where the mass flow scales with the square of the aspect ratio, the effective surface area, and the throughput TP stands for throughput, number of wafers per hour, or something along that line. Of course, this makes sense, at least I hope so, because basically what this says is if you go deeper, bigger, and faster, you need to supply more precursor. I mean, that sounds familiar. This is all still very qualitatively. We can actually, using this mathematics, we can actually calculate how much precursor we need to supply, keep taking into account transport and diffusion and waste and all these kind of things. So as an example, I did some calculations for a lithium-ion battery case. Suppose we have an NMC, nickel, manganese, cobalt oxide electrode for a lithium-ion battery. We want to passivate every individual particle with aluminum oxide using TMA as a precursor, so nothing fancy. Some assumptions: we expect that the cathode thickness is 40 to 50 microns, which corresponds to an effective surface area of, let's say, somewhere between 15 and 20 square meters per square meter. We go for mass production, so we have it's a roll-to-roll process, 1 meter wide rolls, 80 meters per minute web speed, and of course we have to go to double-sided because that's what these electrodes look like. And if you then do the math for this speed with a surface area, we need to supply around 50 grams of TMA per hour per ALD cycle per side. So double-sided, 100 grams per hour. And if you want to do 10 cycles, you need to supply roughly 1 kilogram of TMA per hour. Maxime, I don't know how long you can do with 1 kilogram of TMA here. Yeah.
Or even one? No, I think 5 years.
So this is a lot of precursor, and this is TMA. We're not talking about other fancy, less volatile, less reactive precursors.
We better spend 150 milliliter container.
Yeah. So for a standard precursor evaporator, the limit for high volatility precursors is around 100 grams per hour. So you also need to do something on the evaporation side. And this is, again, for low vapor pressure precursors, this will be significantly more problematic than for something like TMA. It can be solved, but it's not something that you easily do in your lab. So why is this important? Well, what happens if mass flow is too low? Here I plotted the step coverage that you can achieve as a function of the precursor mass flow. So if your precursor mass flow is too low, this means that you do not reach your desired step coverage, the coating depth is too low, and you are something we call supply limitation. You just didn't supply enough precursor to reach the step coverage that you want. And of course, this can impact the performance of your device. You can also have too high precursor mass flow. This means that of course, you cannot go deeper than the pore is deep, so you're wasting precursor. And precursors can be expensive, especially when we talk about iridium and platinum. So you really do want to avoid wasting precursors as much as possible. So what you want to do is, of course, reach this golden point where you supply just enough precursor to just reach the required step coverage that you need to achieve. And that's why this modeling is so important, because we can actually calculate how much precursor we need to supply. Of course, this is a balancing act. Just enough precursor needs to be supplied to reach just high enough step coverage. Consequence of all this is that high volume applications like the battery example I mentioned will only be feasible if you can use high volatility and high reactivity precursors. So choice and selection, development of precursors is very, very important. If you come up with really exotic, low reactivity, low stability precursors that can only be synthesized by a PhD student somewhere in a fume hood, even if the battery performance is excellent, it will never ever be scalable. It's just not possible. So to conclude, spatial ALD, I didn't specifically go into spatial ALD, but of course I work for a spatial ALD company. So I say spatial ALD has big potential for a mass production of next generation sustainable energy technologies. Again, if you want to know more about exactly what we do there, let me know, we can have a discussion. So we focus on things like catalyst coated electrodes for electrolysis of fuel cell, passivation of electrodes for high energy density lithium-ion batteries. These applications and also other examples require coatings inside high aspect ratio and high surface area substrates. This is, of course, where ALD excels. However, it does require exact control of how much precursor we deposit, either because we have to supply massive amounts and you need to be able to handle that, or we work with precursors which are very expensive use scarce elements. So we need to supply just enough to coat all the nooks and crannies of your substrate, but not too much to minimize waste and costs. So bringing ALD from lab to fab is challenging on many levels. I just give you one example in case of the precursor supply. And doing this requires a deep understanding of the ALD chemistry, equipment, precursors, and application. And of course, exchanging knowledge and ideas during events like this is very important to do that. And I would like to thank ATLANT 3D for organizing this event and giving the opportunity to have this discussion. I would like to thank a few of our development partners, especially Air Liquide. I mentioned the importance of good precursors, and they are very good in developing precursors that are very high volatility, high reactivity, and are very suitable to use for these high volume applications. And many of the things we do, we cannot do without their support. I would like to thank you for your attention, and I'm open to take questions.
Thank you very much. So we have some.
I have a very unorthodox question. So if I understand well, so you say it's the square of the amount of precursor you need is with the square of the aspect ratio.
Yes.
Now, if you were to, is it possible to say, I do the deposition of the metal in 4 times? So in this case, I only have to penetrate 1/4 of the distance. In that case, it will take me 1/16 of the time. I have to do it 4 times, but that 4 times 1/16 means that the amount of precursor will be 1/4 of what I would need for a single pass.
I'm not sure if I completely follow your reasoning.
What you see is that you have a square root. The amount of precursor you need is with the square of the aspect ratio.
Yes.
Right? If you were to do, you deposit, and I don't know if it's possible, but I can talk about it. If you go to the picture there, of the metal.
Which one?
The one with the metal in it.
The cross section?
The cross section.
Yeah.
This one?
No, the one with the little grains in it.
More up.
The one with little grains.
That's the lithium battery.
Oh, the battery one. Okay, yeah. Yeah.
So
Is that?
if you would have 1/4 of the thickness of the blue metallish,
Yeah.
you need 1/16 of the amount of precursor. So if there is a way to do metal deposition ALD, metal deposition ALD, metal deposition ALD, you would have 4 steps, but each step would be 1/16 of the amount of precursor. And so you would only need 25% of the amount of precursor you need than if you do everything in one run. And if we're talking about an iridium or a platinum precursor, there's good chance that you can make the financial argument that the people who do apply the metal maybe will be unhappy, but you can strong arm them.
That's a good point. Of course, the surface area, because in the end you still need a 40-50 micron, so the surface area doesn't change. So you still need roughly the same amount of precursor because you need to go to the surface area. It's just that you don't need to supply. The mass flow that you have to supply per stack is lower.
Exactly.
That can be beneficial.
Yeah.
It will have consequences in the other manufacturing steps of that. And
I'm curious about Alex's comment.
Well, so most calendar electrodes are made with a solvent slurry, and so I assume you have to boil the solvent off somehow and evaporate that, which usually takes 1 or 2 days in a battery manufacturing facility. And so that would dramatically slow down production. Destroy that economic argument. But yes, we would use less precursor.
With some chemicals, it might work.
It might work with some chemicals,
So there's a trend in going towards dry processing in the battery fabs. Then it might work because boiling off the solvent is a nasty step. But could be.
Could you please comment the precursor utility efficiency? Because for batch ALD tool, for example, we usually talk about 25%. So like 1 kilo, then 250 gram on the substrate, then the other pump. So what about the spatial?
So there is well, it's not really about spatial or not spatial. It's spatial ALD is also ALD, so same rules apply there. It's a balance between speed and efficiency. So if you go really fast, it's a chemical reaction. To speed up a reaction rate, you can increase the concentration. If you increase concentration, there's more waste and less efficiency. So if you go really efficient, it will come at a cost of speed and vice versa. There are certain tricks you can do. For example, in spatial ALD, we do not deposit on the reactor walls, which already saves some precursor. We can do also tricks to minimize the unwanted deposition. If you really do the math correctly, and if you really optimize your process correctly, you can go up to things like 70% precursor utilization efficiency in the process. 70, roughly. Again, it depends on the speed and the throughput that you need to do. It's easier on a porous substrate to achieve high efficiencies than on a planar substrate. And you can also do precursor reclaim. You can capture unreacted precursor molecules from the waste gas stream, which for things like TMA doesn't make sense because that's bloody cheap. But if you do iridium, then it becomes viable to also include reclaim step there as well. So our target for things like iridium and platinum processes is to go up to 95+% precursor utilization, including the reclaim step.
So for the recycling, is the method like condensation and then collect the vapor pressure with some pump?
In some way, we collect the precursor, and it doesn't end up as a precursor. It will need to be further processed. So we're not capturing the precursor and then putting it back into the bubbler and recycling in one way, because purification is a nightmare. We don't want our customers to do that. But there is a certain way we capture unreacted precursor.
So that means you recycle some precursor, but not directly reuse.
No.
So the chemical supplier can do something,
Yes.
and then
Yes.
and then together up to 95%.
Yeah.
That's great.
Ville had a question.
Yeah, I had a question about the roll-to-roll machine. Has any of your battery manufacturing customers taken that to the production line?
No.
R&D?
It's in R&D phase. Yeah. Yeah. So that's there's a so ALD is not the only solution to this capacity retention problem. There might be others, and yeah, everyone is still developing materials, methods. So this ALD is a promising candidate, but it still needs to be further developed. And so when I talk about 80 meters per minute, 1 meter wide, that's going to be a machine that doesn't fit in this room. So it's and before we decide to invest in building such a tool, we need to do a lot more technical loopholes to go through.
And it's also the kind of thing that you don't make a prototype if you don't have a purchase order.
Yeah, exactly. Yeah. Luckily, we have a purchase order for a pilot tool.
Oh yeah, nice.
So that's what we're going to start building very soon, but not for 80 meters per minute. That's more. Yeah.
I'm curious, practically, given your massive volumes of precursors you're using in designs like this, how do the pumps hold up, and how do you
We don't have pumps because it's atmospheric pressure.
Oh, okay. Thank you.
Yep.
Thank you for supporting atmospheric.
Yeah.
I'll just add this is one of the technologies that directly complementary with ATLANT technology, because this is the same principle that we applied at ATLANT, but just in centric rings in the micro nozzle, and they have a print head which is like running back and forth, or actually the stage move, right? In your case as well.
Yeah, it's essentially the same technology. It's just a different application, different scale, but essentially it's the same technology. Yeah.
All right. Well, thank you very much.